Welcome everyone to Design with Climate, Form Follows Performance. So we're going to talk today about energy efficient design, passive design, and zero carbon buildings. We have three presenters today and panelists. First is, I'd like to introduce Pablo Roche. He's the Global Sustainable Design Leader for CalllisonRTKL. He's also a professor of architecture and interim director of the Lyle Center for Regenerative Studies at Cal Poly Pomona University. Second up is Gerardo Velázquez Flores, and Gerardo heads a design studio called Bioarquitectura. They design projects all over Mexico. He also teaches at the Ibero-American University, and he recently published a book called Sustainable Retrofitting of Buildings. And last up, who'll be the first one to present, is Alfredo Fernandez-Gonzalez. Alfredo is a professor at the University of Nevada, Las Vegas School of Architecture. He's also founding director of the National Energy's Advanced Technologies Laboratory at the university. So I will now pass it over to Alfredo to lead us off.
Thank you very much, Ed. Hello, everyone. And in this session, Pablo and I will talk to you about climate-based design. And here we go. For architectural design purposes, a climate classification that addresses the challenges that we face to deliver thermal comfort is what is really needed. And as human thermal comfort depends on the dissipation of the body's metabolic heat, discomfort will occur when there is insufficient or too much heat dissipation. And as we are reminded by Jim Augustine in his wonderful book, The Return of the Solar Cat, buildings should recognize the influence of the climate and really take advantage of passive design strategies, which is the focus of this session. Since solutions need to emerge from place, in this session we will use a climate classification that addresses the thermal issues associated with the provision of comfort. And for convenience, we have grouped the ANSI ASHRAE Standard 169 in 4 different categories: hot, humid, hot, dry, temperate, and cold climates. Here, using the bioclimatic chart as a reference, we can see the approximate range of conditions of our 4 climate zones, the ones that we've just defined. And if you're not familiar with the psychrometric chart, on the horizontal axis, you have dry bulb temperature. On the vertical axis, you have absolute humidity, and the curves that you see inside the psychrometric chart correspond to relative humidity information. So the temperature and humidity range of the temperate climate zone is generally associated with thermal comfort, and therefore the upper and lower limits of this temperate zone are really important from a design perspective. So the red line that just appeared corresponds to what we would call the shading line. And the shading line suggests the times when we need to begin implementing shading, both for our windows as well as outdoor spaces. So when the temperature rises above that red line, shading becomes necessary. The blue line corresponds to the upper limit of the temperate climate zone, and this constitutes the cooling line. When the temperatures rise above that cooling line, some form of cooling needs to be provided to achieve thermal comfort. So this, again, is initial reference. I want to plug in a fantastic resource, which is developed by Professor Murray Milne at UCLA. This is a climate consultant, a program that allows you to very quickly conduct a climate analysis of really just about any location on Earth. And here you see appearing those 2 lines I had just mentioned before, the shading line and the cooling line, on the psychrometric chart for the city of Las Vegas. And the box which you see on the upper left gives you the percentage of time in which conditions fall within a given passive strategy. So that's how we can make conditions comfortable. So let's talk about cold climates. And cold climates typically occur at latitudes that are higher than 40 degrees north or south from the equator, or at very high elevations greater than 7,000 feet or 2,100 meters above sea level. And in these kinds of conditions, a well-insulated building is a prerequisite. In addition, solar radiation, gain, and thermal mass are both needed to achieve thermal comfort. So let's talk about the form that buildings should pursue in cold climates. So we'll basically through some series of quick slides. A building elongated along the east and west axis provides the best performance for winter heating, but also for daylighting and summer sun shading. And as a general rule of thumb, a building width should be approximately 5 times the floor to ceiling height. So if windows are available on both sides, this allows for excellent daylighting distribution and ventilation during the summertime. The length of the building should be as long as reasonable. If a building gets too long, consider making it 2 or 3 stories higher or as tall as needed. In the Northern Hemisphere, during the winter time, a building elongated along the east-west axis will expose its roof and south facade to incoming solar radiation. Correctly placed fenestration along the roof or the south wall will allow for passive solar heating during the winter. And in the Southern Hemisphere, we would aim to expose the north-facing roof and facade to incoming solar radiation. During the summer, it's critical that we provide a properly sized overhang to provide the shading to the windows that were used for winter sun collection. Remember to keep the east and west facades, along with other certain roof areas, shaded as possible, so that, in spite of the fact that this will receive the largest amount of radiation, they need to be protected in the summer to avoid overheating of our building. I also want to plug in a very important resource, which is the Architecture 2030 palette. The 2030 palette provides you with tremendous resources to provide initial guidelines during the design process. And today I just want to show the example of sizing windows for direct gain. And when you click into this strategy, then you will see, among the many pieces of information there, you will see a very detailed guideline to size windows, to size glazing for passive solar heating. So continuing with the form for heating in cold climates, the form that is narrow, the floor plate that is narrow, it's also critical for successful natural ventilation when this is considered. This allows us to effectively ventilate the building, having windows on both sides. To enhance the performance of cross ventilation, one of the building's long facades should be oriented as close to perpendicular to the prevailing wind direction. The compromise between winter solar heating and natural ventilation may be obtained by rotating a building up to 30 degrees from the equator facing orientation. Heating and cooling requirements need to be considered before making the final decision. And in spaces with a floor plan, partitions should be oriented perpendicular to the windows for better daylighting penetration, as well as to maintain adequate airflow during ventilation mode. Now I'm going to show you a case study of a building which is net energy positive. In fact, this building produces more energy than it consumes on a yearly basis. The building is located in climate zone 7B, and it's located in Basalt, Colorado. Here are some relevant parameters about this particular building. And I want to emphasize the building form follows the east-west axis. Recommendation we just made has a very narrow floor plate, butterfly roof with higher ceiling near the windows to maximize daylight penetration. And it has obviously a highly insulated envelope following passive house standards, and large south-facing windows to provide passive solar heating with active solar gain controls. So here you see the elongated plan along the east-west axis, and a window-to-wall ratio of 52% on the south versus 18% on the north. So windows maximized for daylighting, ventilation, and passive solar heating. The narrow plan permits also the penetration and good distribution of daylighting. And that same narrow plan also allows for successful natural ventilation of the spaces during the summertime. The building maximizes passive solar design and is really insulated to meet passive house standards. Also to improve, as we mentioned, to improve both daylighting performance and passive solar heating, the building features a butterfly roof to have a higher ceiling near the windows, particularly the south-facing windows. And in addition, to minimize glare and to control solar heat gain, the building features automated exterior sunshades. This is a view of the south facade without the south-facing window sunshades deployed. And this is a view with the automated window sunshades deployed to control glare and solar gain. Thermal mass in this building is used to both absorb solar heat gain in the wintertime and to pre-cool the building at night during the summer for improved comfort during work hours. And here you see the smaller photographs on the right show the circulation area provided near the south-facing windows, which creates a thermal buffer zone. And through the addition of the lower bookshelves, you also see here, these bookshelves serve as partitions, but they also reduce glare on work surfaces when solar radiation is coming through the windows. By contrast, in the lobby area, where we don't perform visual tasks, we have solar radiation absorbed directly by the floor slab, and very vibrant and open space where solar radiation contributes to the heating of it. And finally, natural ventilation during the nighttime allows the building to fully maximize its thermal mass throughout the day. Taking advantage of the cold evening temperatures, the building automatically opens the windows and cools the internal slab to keep the building cool through the next day. On summer days, when appropriate, the occupants of the building may open the windows to cross-ventilate this building. Windows on the north sides are operable, and they are also appropriately sized to minimize heat loss and also to help achieve appropriate illumination and cross-ventilation. Again, an excellent example for a cold climate. Let me now talk about hot, dry climates. And hot, dry climates typically occur between the latitudes of 10 and 40 degrees north or south of the equator. They're characterized by limited precipitation, clear skies with intense solar radiation year-round, and large temperature variations between the daytime and the nighttime. A form of cooling is needed, as we mentioned earlier, when the temperature rises above the temperate climate zone. In warm, dry climates, we have the options of nighttime ventilation when the temperatures at night go below the comfort zone, or we can also use evaporative cooling as a means to provide thermal comfort. A form of cooling, as we mentioned, will be needed in this type of climate, but the biggest imperative during the summer is to reduce heat gains through windows and roof surfaces. The use of external shading for windows, the provision of vegetation, outdoor shading, as well as water features may help create microclimates that are conducive to outdoor comfort and become some of the most important strategies that one can use in this type of environment. I want to highlight that in this type of climate, the urban form also plays an important part in the cooling strategies process. In hot, dry cities and towns developed prior to the 20th century, urban form was uniquely developed to maximize shade of the walls and windows as well as those public outdoor spaces. This is an aerial photograph of Grazalema in Andalusia, Spain. And here we're going to see a couple of images, one of the main plaza and also a narrow street adjacent to it. And we can see in these photographs that in the main plaza, those windows that are exposed to more open spaces have overhangs, as well as other forms of shading, blinds, etc. We also provide additional shading through the umbrellas and trees for the public outdoor spaces to be usable and also comfortable. Also notice the light color in the building facades. And on the photograph on the right, you can see a narrow street, typical of this kind of climate. The remains cool during the daytime because it's in deep shade, surrounded by heavy mass materials. And we gain illumination, ventilation, and privacy, all through the use of courtyards as a strategy in this type of climate. So here you see the vegetation, oftentimes evaporative cooling also deployed, having shade through the movable toldos and awnings. And of course, we can ventilation and cooling that way. So I would like to show you an example of a really nice building here in the United States, in Springdale, Utah, with climate zone 3B. It's the Zion National Park Visit Center. And here are particulars about this. Among the most important things, the L-shaped building form with larger facades facing the south, a narrow floor plate, high clerestory windows for daylighting, and lower windows for view. In terms of heating, the use of trum walls and direct gain for passive solar. And also for cooling, we have downdraft evaporative cooling towers, also called cool towers, for direct evaporation during the summer. Here's a diagram of the building. We can see that the form is elongated along the east-west axis, much like in the cold climate. And a narrow floor plate permits the appropriate distribution of daylighting and successful ventilation. And in the wintertime, the trum walls on the south side and the high clerestory windows provide the space heating. Appropriate shading for these windows is also necessary during swing seasons to prevent overheating. So here you see a photograph during the spring season. I actually just visited the site this spring, and you can see that the trum wall is partially shaded as well as the clerestory windows. But during the summertime, when shading is an imperative, the windows are fully in shade to avoid overheating.
Alfredo, we'll need to start wrapping up to move on to Pablo's presentation.
Yes, thank you, Vince. I'm wrapping up just now. So we have the cool towers to provide the necessary cooling and ventilation in this space, and the clerestory and south-facing windows are used to exhaust the warmer air. So you can see that we can take hot, dry air, add moisture to it, and cool it, deliver it to the spaces below. This photograph under construction. And the cooling towers, or the cool towers rather, provide a fascinating and exciting experience to visitors and successful ventilation and cooling of the space. And with that, I'd like to hand it over to my colleague, Pablo Roche.
I'm going to talk about hot and humid climates. And as we saw, we divide the climates in 4 zones. I'm going to talk about the ones that are closer to the equator, low altitudes, low latitudes, and in which we have high humidities and lower differences between the day and night. These are, if we look at the psychrometric chart that Alfredo showed, they're going to be towards the right and towards the top of the comfort zone, which is sort of this area. It's always helpful to understand climates by looking at where the data is in the psychrometric chart. And what we do, hot and humid climate is going to be warmer outside and more humid than the comfort zone. And it's necessary to keep the building from overheating first and then cool it. And we typically will do this with shade, which reduces heat gains, and natural ventilation, which can evacuate the hot air from the interior of the space. An example of a hot and humid climate would be, for example, San Juan, Puerto Rico. And you can see that most of the year, we are, if not all of the year, pretty much we're towards the right and the top of the comfort zone. We can also see that recommended strategies are also, if we look at climate consultant, are natural ventilation and shade. What is the typical response for buildings in hot and humid climate? It's a thin plan in which you are maximizing cross ventilation and you're providing daylight also. And the smallest facade is towards the east and towards the west. Close to the equator, the sun rises close to the east and sets close to the west, and then spends a lot of time overhead. So the roof is really critical, which must be insulated and providing extensive overhangs. And this shade reduces heat gains through the envelope. If we look at the vernacular response in different climates all over the world, in different hot and humid climates all over the world, we're gonna see common traits. Again, we're providing shade, we're providing permeability through the walls for the air to move, and we're providing some protection from the rain. If we look at the early 20th century response from oil companies that went to the tropics or fruit companies, very interesting proposals, very simple in their conception. Again, we're going to go above the ground to protect from critters and also to provide more natural ventilation. We're also providing more shade above us, more shade with these hats around their buildings. Looking at the layout of these buildings is also important, and they're maximizing natural ventilation, air movement between the buildings, and shade also in these outdoor environments. Now, speaking of outdoor environments, we can also make them better. Traditionally, we're providing shade and air movement, but in this project that we developed in the office at CalllisonRTKL, we're going a little bit beyond that and also thinking of radiant cooling. Can we connect liquid-filled tubes embedded in the soil of the planting material that we cool with the earth, we cool with evaporation on top of it, and then these tubes cool panels that are cooling by radiation at the occupant level and at the lower level. And we've done several tests with different types of green roofs. This was developed for a project in Jakarta in a hot and humid climate. And again, we're trying to maximize outdoor comfort by understanding the processes that affect thermal comfort, sort of what Alfredo mentioned in the beginning. And when you combine several of these together, we're not only improving comfort below, but we're also reducing the heat island effect. So multiple combinations of these elements reduce the heat island effect. So in a hot and humid climate, when we think about the envelope, we're have to block solar radiation from the sun, block conduction, and maximize ventilation. When we think of these strategies in architectural terms, we're thinking of maximizing shade, maximizing air movement when appropriate, when it's cooler outside and inside. We're using cool reflective surfaces or maybe even vegetated surfaces. We're reducing heat gains through the building fabric, which is typically done with insulation. And we're reducing the heat gains around the building using shade and cool surfaces. So it's all about reducing these heat gains. And then we can maximize air movement, which is going to remove the heat from the interior of the building and also improve thermal comfort by improving this sweat evaporation from our skin. Shade, there's rules of thumb for shade, but I always think that it's important to understand, develop some sort of workflow and understand climate. So do a climate analysis first. Of course, if it's always hot, we're always going to need shade, but there is some need for heating during the winter, or there's some sort of heating requirement, then we have to understand that we don't need shade all year. So we have to define these periods. We have to look at opportunities. Let me show this here a second. So we got to look, we can do a solar study in which we can find critical facades. We can use climate consultant, another tool to find the required vertical and horizontal shadow angles. And then we test these while we develop a system that we can test for daylight, for glare, for solar gains, and for energy. If the shade system works appropriately, we go on with the project. If not, we go back and we develop another proposal based on these rules. So again, it's really about understanding climate and developing a response that is architecturally working with the building. An example is, this is students at CallPoliPomona School of Architecture at the Lao Center, working together, developing a proposal for Barranquitas in Venezuela. It's really about a roof that is floating above you and then air movement down below. We can also use this in, we're not limited to small buildings, right? We can take these concepts to other types of buildings, to high buildings. So in this office building in Shenzhen, we're looking to open it's for a competition. We opened to the interior to maximize air movement and maximizing daylight. Again, we test these ideas with building simulation. Very important to test ideas with software to validate the ideas. We're looking at exterior solutions. Again, through this courtyard, we're maximizing airflow and maximizing daylight to the interior of the office spaces. And then we have a building that is responsive to a hot and humid climate. Airport terminal and Terminal 2 in Guadalajara. This is also, it's a hot climate. And when we look at conditions in the psychrometric chart, we're not a psychrometric chart, sorry, in a temperature, we see that we need shade during all year, and we have a higher solar radiation period from March to July. Again, it's sort of looking at how we control these heat flows, right? How we provide shade, how we block conduction, how we increase long wave radiation through cool roofs, how we have maximize daylight and reduce glare. So just to show you a little bit of the studies that we do. So this is a west-facing facade, right? And which we have to really control the heat gain and the glare. So what we do is that we select a portion of that facade. We don't have to study the whole facade. And then we, architecturally, the design team wanted to have something expressive, which is an overhang, which is also reducing, if we look at the heat gain, from about 800 kilowatt hours per square meter to about half of that, about 400 kilowatt hours per square meter. Then we added frit. When we study glare, we're looking, this glare study is showing you, this is a person sitting in the waiting area, looking outside towards the west, looking at his plane to see if it arrived or not. And then if we have no shading, we have quite significant glare. When we add the overhang, we're reducing the glare. And if we add some frit on the glass, we're almost completely reducing the glare effects for a couple of hours in the late afternoon. If we look at, we did an extensive study of the envelopes just to show you how this works. You know, we studied that period that I showed in the beginning, and we found facades that might have more of an issue, and then we do an architectural response to that facade, right? So we still maintain transparency wherever possible, but we add a little bit more shade in those areas that are more critical. And then we can provide some shade, we can provide some daylight, we can provide views, and still have that control of the heat gain through the envelope. If we go to a temperate climate, conditions are towards close to the comfort zone. And it's really interesting because it's in the summer, it's a little bit warmer than comfort and a little bit cooler in the winter than comfort. So what we need to do is to keep the building from overheating with shade in the summer and cool it with natural ventilation. And in the winter, some sort of passive heating will help. An example is Los Angeles, California. You can see the comfort zone, and you can see that we're pretty close to the comfort zone all year, and some passive heating and natural ventilation is going to help. If we look at the examples, the building response, I would really emphasize sort of this equatorial facing orientation in which we have an overhang. And so we can provide some summer protection and some winter solar gains. And ventilation, it will be helpful when it's cooler outside than inside. We look at the responses. One of my favorite is, Rudolf Schindler, 1921. Really, he started with this whole movement of sort of connecting the indoors and the outdoors. Almost very thin walls, work very well in the summer, but not as well in the winter. But again, these are operable. Lots of examples in California, in Southern California especially. And this is the VDL Research House owned by CallPoliPomona, built in 1932, and then burnt down, rebuilt in 1964. But again, it's natural ventilation, it's shade, it's daylight, a courtyard. Again, sort of understand these climate forces and a little bit of evaporative cooling. I've had reviews here, and it's really nice to sort of feel how the day changes as you're in the space. You can have, it's naturally ventilated. It might be a little bit cooler in the morning, then a little bit warmer, but you're feeling these forces, you know, this sort of change, this haptic changes during the day, which is actually quite pleasant. And then when we think about the heat flows, is really blocking the summer sun and providing some winter heating. So it's very similar to, so there's some protection in the summer and then some allowing of the heat in the winter. An example, I'm just going to show you quickly a couple of examples. One of them is in Tenerife in Spain, is really a project that we developed in which we looked at wind coming from the north east to orient a part of the building, and then solar geometry to orient the other part of the building. And then in the intersection of these two, what you see here is a wind scoop that is providing airflow and natural ventilation to the building. So we have
No, John, I still will need to respond to questions.
So we have ventilation during the summer.
We still have about 15 minutes.
So we still have ventilation during the summer, and then we're blocking the heat during the summer also, and providing some heat gains in the winter. If we see a section of the project, we're looking at, it's all about having the air move through the space, right? And there's even in the upper part of the living room, there's the air, we're inside the wind scoop. The air passes from above us through the living space down to the first floor. Sort of, we're really connected to the forces of nature, to the wind and the sun. The south-facing facade, we don't have a large overhang, but we have operable elements that that slide and provide shade. And this has been monitored by ITER, Instituto Tecnológico de Energías Renovables. And it's really interesting to see the conditions outside are very close to comfort, but the conditions inside are also, this is inside, this is outside, are very close to comfort also. No mechanical heating, no mechanical cooling, and it's just cooled and heated by the forces of nature. So we can see that it's really understanding these principles that can have you operate a building appropriately, opening and closing as required. And this is the last case study. Just quickly, I wanted to show you how using also multiple tools, we can also improve performance in a building. And this is working with our London office. It's a project in Milan, northern Italy. And again, we start with sustainable design, really sort of understanding the climate. We're looking at design ideas shared between sustainability and the design team. And then we have a computational design team also testing these ideas and generating different forms that are tested with rules generated by the sustainability team. So this, and then at the end, there's a validation and testing of these options. So again, we're looking at climate, generating ideas, sketching together, looking at a form that is responsive to the sun and the wind, testing different angles and different tilts and different orientations, finding in a north-south section, which is the critical one in the summer and the critical one in the winter. In the winter, we want to maximize radiation. In the summer, we want to block it. This is going to show us quantitatively with a solar study, and then translating that to a geometry that is tested also with different types of louvers, and to find the best option, to find the best fit. And then tested for energy and for daylight. So the idea is the same design team in London generated this project in Australia. The idea is that we generate an interior space that is responsive to the outside, but it also enriches the experience on the interior. So just finally, so what should we do when we're talking about carbon neutrality in buildings? I think Alfredo and I would say that we should always respond to climate first. Climate responsive buildings cool and heat without generating CO2. They reduce the building's carbon footprint and are exciting because they offer design opportunities. Thank you.
Okay, hello everyone. Can you see my presentation? Okay,
Yes.
thank you very much, Edward, Alfredo, and Pablo. I'm going to present a case study of the M16 building I designed some years ago. So we have a great and sustainable opportunity to change the face of our cities through existing buildings. I came across this building 50 years ago. It's a building, a 50 years old building, and I did a retrofitting. And whenever you do a retrofitting, you have the opportunity to identify problems like overheating, noise, underheating, accessibility. So this is the location of the building in a beautiful street full of trees. And this was the previous condition of it. We detected opportunities for bioclimatic strategies in these two patios in the back of the building. And we always start our analysis with a 3D image where we can map the prevailing winds, sun path, views, noise, in order to propose a responsive building. We start by studying the hourly temperatures and the relative humidity by hourly, and overlapping those temperatures in a sun path to know what temperatures are when the sun is in certain position. So some of our strategies were to use a solar chimney, a warm greenhouse, and a cold greenhouse. So for the cooling system, we use the cold air from the cold greenhouse. So we pass it through the building and exhaust it from a solar chimney. And for the heating system, we use a warm air from the hot greenhouse. We had the higher intake, and we pass it through the building. In terms of energy efficiency, we use photovoltaics, two-ways electric meter, and it's interesting to notice that the embodied energy for this retrofit was 1/3 of a new construction. In terms of water management, we harvested rainwater, and we use evaporating cooling for the cold greenhouse in the hot season. In terms of building skin and materials, we use in nature to protect the sun from the sun in the overheating period. So this is the before and after of the building. And it's interesting to notice how we control the solar radiation in the overheating time for the western facade only with vegetation. For natural lighting, we normally have this kind of patches of darkness in the middle. So there were not enough luxes for this area. So we put light wells in the building to get the lighting inside of the building, and letting the light inside of the middle section of the building and with some light shelves. So this is the before and after of the analysis, where you can see how the lighting was improved. So this is how it used to look like. And this is only natural lighting, what you're seeing right there. So no electric lighting there, of course, for backup. And we could have even zenithal shadow. So that was something quite nice inside of a building. This is the higher level. So you can see here how the light wells go through. And about, in terms of beauty, I would ask you, what is more beautiful than nature, right? So instead of having these views to the exterior for the users, we had these kind of views to the greenhouses. And we received the Platinum LEED certification, being #1 in Latin America and 12 in the world as for March 2015. So I decided to publish this book with all the strategies we use, and this book is available online. And I'm sorry that this was very fast, but we had little time. Thank you very much, Edward, again, and I'll go back to you.
Yeah, thank you. Thank you very much. We ran over a bit, so we do not have time for Q&A. There's been a bunch of Q&A and quite a bit of interest in this session. We've had over 400 people participate. So we will record it and then and put it up live. We'll also show it again in 2 different climate zones, and time zones in a week, and then in 2 weeks again. So hopefully we'll get everybody's questions answered online, and we'll have the full video available online and in the next two sessions. So thank you very much, everyone, for attending, and Alfredo, Pablo, and Gerardo, thank you for a very enlightening session.